Sure.
Great. So it's a great pleasure to welcome you all again to our combinatoric seminar. It's a great pleasure to have today Matija Bucic from Institute for Advanced Study in Princeton University and also in the past from Zurich. And he will talk about essentially tight bounds for rainbow cycles in proper edge colorings. Please, Matija.
Yeah. So thank you very much, Benny, for the introduction. Thank you for the invitation to speak in the seminar, and thank you all for coming. So as Benny said, I'll tell you something about the problem, which I like to call the rainbow to run problem for all cycles. And it's a question I really like, and that has attracted quite a bit of attention in the area in recent years, and also has some nice applications that I'll also tell you a little bit about. But let's start at the beginning. So I'm calling it a to-run question. So what do I mean by that? So a general to-run type question asks, how many edges do we need to have in a graph in order to guarantee that we can find a certain structure inside of the graph? So usually this structure is just some single graph that we're looking at, but over the years, people looked at a wide variety of variants of this, and there are many examples of this type of question that go beyond just looking for a single graph. So I will also be switching between the two equivalent versions of stating this question. So the second one is just asking what average degree do you need to have in a graph in order to guarantee this structure. So you can easily switch between the two, and I'll be switching without mention, depending on which one makes more sense at a given time. So just to have a concrete example in mind, so here is one of the most classical results in extremal graph theory. It's called Mantel's theorem, and it says that in order to guarantee a triangle, you need roughly n²/4 edges. Now, over the years, this has been generalized in a very wide variety of ways, but perhaps the most classical one was looking at the triangle as a clique of size 3, and then what the natural thing to ask is, how many edges do you need to find larger cliques? Okay, 4 and so on. And this is the subject of Turan's theorem, which is the namesake of all of these questions, and essentially, in some sense, almost all of this part of extremal graph theory. And the Turan theorem tells us the answer to this question if we want to find a clique. And there is also the theorem of Erdős and Stone, which tells us the answer asymptotically if we want any graph which has chromatic number at least 3. And in some sense, these instances we understand because the answer is quadratic. So the graphs we're working with are dense. So we have a variety of tools that we can use and play with and understand these problems much better than the counterpart bipartite case, in which the answer is sparse in some, so it's little of n², where much less is known, and there are many, many very classical open problems. In particular, another generalization of Mantel's theorem is to look at the triangle as a cycle of length 3, and then you're just looking how big a cycle, well, for an cycle of arbitrary length, how many edges do you need to have in order to guarantee it? So for odd cycles, the answer is the same as for the triangle. This is part of Erdős-Stone. And for even cycles, there are many open problems. We only understand it for a few values of the length. So the starting point for today is going to go in this direction, but it's actually going to be a very easy observation that features in almost any introductory course on graph theory. And this is that if you have average degree of at least 2 in a graph, then you can find a cycle. So here we don't care about specific length. We just want to find a cycle, some cycle in our graph. And this is very easy to see because in the other formulation, it's actually saying that as soon as you have n edges in your graph, you are no longer a forest, so you can find a cycle. Now, this is, of course, a very simple example, but it's something that we tend to use without mention quite a bit, and it pops up, and it's quite a useful, simple, easy observation. So where we're going today is we are going to be looking for, in some sense, special cycles, motivated in part by applications, but also because it makes for a natural general collection of questions, which were introduced by Keevash, Mubayi, Sudakov, and Verstraëte in 2006. So they asked what is referred to as a rainbow to run problem. And what is going on is we are again asking what average degree do we need to have in a graph in order to guarantee that we can find a rainbow copy of the structure we're looking for in any proper edge coloring of the graph G. So there are two modifications happening here compared to the general Turan problem. The first one involves the proper edge coloring, which, just to make sure we're on the same page, refers to a coloring in which there are no two edges of the same color which share a vertex. So here is an example. And the second part involves rainbow colorings, which are just colorings which don't reuse colors. So here is, for example, a rainbow copy of a cycle of length 6. So what is going on in this question is you take your favorite Turan type problem, and then your worst enemy comes and colors your ground graph in some proper edge coloring, and your task is not to find just the structure you're looking for. You actually want to find it to be rainbow in this proper edge color. So the original motivation for this came from some nice applications to additive number theory, but also because there were several similar questions that were popping up in the area. And it is also quite a natural question. And I think I really like the kind of perspective on it, which says that it's in some sense a very anti-Ramsey problem. So Ramsey theory refers to a large body of results, which all, roughly speaking, say that in any large structure, you can find a well-organized substructure. So in coloring problems, that usually means we're looking for monochromatic objects. And here we are looking for rainbow objects. So in some sense, as chaotic objects as you want. However, the problem is, well, you will not be able to guarantee chaotic objects in any large structure because your large structure could just be monochromatic. So you have no rainbow objects. So what's going on with the proper edge coloring is you're putting some sort of local chaos assumption. Namely, at every vertex, the star at this vertex should be rainbow. So that's a little bit of a local chaotic assumption. And what you're looking for is you want to lift this and be able to find some more global chaotic structures like these rainbow cycles or various other rainbow objects that you are interested in or that are popping up in your problem. So we'll see two examples of kind of where this type of proper colorings come up very naturally, and also finding rainbow objects is also quite natural. But let me just mention also the Reiser-Brualdi-Stein conjecture, which has had some very exciting recent developments due to Montgomery, in which we are also working with proper edge colorings and looking for rainbow matchings. It doesn't quite fall under this paradigm, but it's playing with the same type of objects. Very good. So this is the question we'll be looking at. And as I said, we are going to look at the rainbow variant of this easy observation, which is asking how many edges do we need to guarantee a cycle. So now, instead of looking for just a cycle, we actually want to find a rainbow cycle in any proper edge coloring of our graph G. So this question, among many other very interesting ones, has been raised already in this paper from 2006. And it turns out to be quite a bit more interesting. So in particular, the lower bound does grow with n, and it's growing at least as fast as log base 2 of n. And this is thanks to very simple construction. You just take the hypercube graph of dimension log 2n, and you color all of the edges that go in the same direction in the same color. So this is a proper edge coloring of a graph which has average degree log 2n, and it has no rainbow cycles because as soon as you move in a direction, you're restricted to that part of the hypercube, but you need to go back eventually to close the cycle, which means you will need to reuse the color when you go back to the original part. So there is a bit better construction than this that was already presented in the original paper. It's based on taking some sort of Cayley graphs of the symmetric group on 3 elements and taking products of this. And it gives something like 1.1 times log 2 to the n, but I'll not explain in details how that construction actually works. So this is as much as we know about the lower bounds. So, and it's very interesting to try to improve them. I think it might be possible to even get something growing. I'll say something more about that later. But what I want to focus on today are the upper bounds. So in the original paper, Keevash, Mubayi, Sudakov, and Verstraëte got n to the 1/3 as an easy corollary of a specific instance of this problem where they were looking for a fixed length cycle. And the first improvement that got this to a sub-polynomial bound is due to Dasli and Sudakov, who got e to the root log n bound, and this was using some expansion ideas. Then the first polylog bound is due to Oliver Janzer, who got it down to constant times log to the 4n in the paper which introduced his homomorphism counting approach, which has found also some very impressive applications since then. And then Istvan Tomon got the exponent of the polylog, improved the exponent of the polylog, and went back to using expanders. So he proved that log to the 2 plus little of 1 times n is enough. And then 2 independent papers by Janzer and Sudakov and Kim-Lee-Liu-Tran went back to the homomorphism counting and removed the little of 1 of n here, which I think is interesting because at the time, and I think that this log squared n is really the barrier. So this was showing that kind of both approaches that were floating around hit this barrier at log squared n. And actually we spent equal amount of time trying to improve the lower bounds and upper bounds while thinking about this problem. So what we do in a joint work with Noga Alon, Lisa Sauermann, Dima Zakharov, and Zamir is show that the answer to this question is actually log 2n to the 1 plus little of 1. So in particular, we improve the upper bound to some constant times log n times log log n. So if you take any properly colored n vertex graph, which has average degree at least this, then you can find a rainbow cycle inside of it. Very good. So let me mention some nice applications of this theorem. So one of them I will just say in words and not go into too much details. And for the other one, I will go into a bit more. So the first one comes from discrete geometry. And the basic idea is if you take some endpoints in, say, the plane or R to the D, you can define various relations between these points, which is something that has been studied a lot in various questions in discrete geometry. So for example, let me be concrete and say that we put an edge between 2 points if they're at distance 1. So now you have a graph whose vertices are these endpoints, edges are pairs at distance 1, and it actually comes with a fairly natural proper edge coloring, which just keeps track of the directions of the unit distances that you're getting there. So now keen-eyed among you will notice that this is not technically a proper edge coloring because you could have at the vertex, you could have 2 edges which are of distance 1 and parallel, and so they would get the same color. But if you pay a factor of 2 in this setting, in the number of edges, you get a proper edge color. So now, if you have a lot of unit distances among these points, then you can use our result, or actually also the previous ones. And but if you use our result, you can precisely recover a result of Matuszek from 2011, in which he was studying this problem, this unit distance problem. So how many of the unit distances you can have in the so-called typical norm setting. So I'll not go much more into details about that. I just wanted to give you a picture of some geometric setting in which this thing turns out to be also quite nice. And I'm not going into much more details because we managed to get much more precise bounds and are not really using the rainbow cycles there. But somehow the 2 problems are related. It's just that the geometry gives us more power so that we don't necessarily need to find rainbow cycles, but some other objects are also fine. And this gives us enough power to get rid of this log there and even determine the correct constant. Now, for the other application, which goes into the additive number theory direction, I do want to tell you a little bit more about because I think it's very interesting and it's a simpler application, so I can actually tell you how it works. And it's also some notions which I was not really aware of, but that seem to be floating around quite a bit in the additive world. So the notion that we will need is the notion of a dissociated set. So given a group, if you take a subset of its elements, we say that this subset is dissociated if it contains no non-trivial relations between the elements in the set where the coefficients are allowed to be 0, 1, or -1. So what I mean by a coefficient 0, I mean you just don't take the element in the sum. By coefficient 1, I mean you just take it. By -1, I mean you take the inverse. Okay, so I'm writing here plus because I want you to initially at least think about this in terms of abelian groups, where it's actually quite a simpler statement, because in the abelian group, you can just move everything with a -1 to the other side. So this becomes equivalent to saying that all subset sums are different, because as soon as you get the same subset sum, you get a non-trivial relation in this setting. The reason I'm stating it in this linear algebraic way is because it works equally as well also for non-abelian groups, which is something I will say a little bit about, and which is the direction we're going in, but also because this is in some sense the reason why these dissociated sets turn out to be quite useful, both in harmonic analysis, so they appear in this book of Rudin, and also in additive number theory. There are quite a few papers using this type of ideas. So the reason they turn out to be useful is that they are some sort of poor man's version of linearly independent sets in vector spaces. So in vector spaces, you would just define linearly independent set of vectors in the same way, except you would allow coefficients to be in your multiplicative field. So in arbitrary groups, we don't have this, but we always know what multiplication by 0, 1, and -1 is in terms of what I said before. So in some sense, these dissociated sets give you similar amount of power, give you similar amount of power as linearly independent sets do in vector spaces. So they're actually weaker in various sense, but they do keep some nice properties that you get from linear independence. The first one being that if you take a maximal dissociated subset of some set in your group, then this set is spanning for the set. So this is, again, very easy to see. If it's not spanning, then you could just, whatever you're not spanning, you can use to extend your maximal dissociated set. You just move it to the other side. The second property, which was proved by Lev and Euster, at least in the abelian case, says that actually maximal dissociated sets have similar sizes. So in vector spaces, they would have the same size, and this size would be called the dimension. So with dissociated sets, we don't quite have as much power, so they will not be all of equal size, but they will only differ by some polylog factors. And so with this in mind, Shen and Shkredov actually defined a notion of dimension that works in arbitrary groups. So they call it the additive dimension. And it's defined just as the size of a maximum dissociated subset of the set you're working. So dimension of A is the maximum size of a dissociated subset of A. Very good. So I'm just repeating the definition because it wasn't on slide for long enough. So now let me mention a result which actually precedes the definition, but it's a nice theorem of Sanders and Shkredov from 2007. But if you translate it into these notions that were introduced a bit later, what it's saying is that if you take an abelian group and you take a subset of it which has small doubling, so if you take all pairs of elements and you take their sum, then you're not seeing many different elements when you do this, then actually the dimension of your set should be small. So what this is saying in some sense is that sets with small doubling should be reasonably structured in the sense that they should live in a small subspace of your group, where subspace comes with quotation marks. So, and this type of questions are actually one of the main type of questions that have been studied quite a lot in additive number theory. So namely, trying to understand, like you have two cases, you have good expansion or you have small doubling, in which case you should be in some structured case. So there are quite a lot of results of this flavor, classical ones, which are establishing structures on sets which don't expand well in some sense.
Matija, so it would have been not for set, just for the whole groups, and the fact that the dimension is logarithmic, it's immediate from more or less your definition, right?
So you can get it, yeah. I mean, there are like, you can just follow all the paths, and yeah, so there is a very simple thing if you do it for, but for a specific set, you like they are using some Fourier analytic things, and there is a way of getting around it, but I mean, you anyway. So, but yeah, you are correct. If you take A to be the whole group, this is fairly easy, and you even get log 2n, and this is precisely correct. It also has a name actually for the whole group. It's called the plus minus Davenport constant, which has also been studied in different directions, and quite a lot is known and quite a lot is not known. But in terms of general upper bounds, there you get log 2n precisely without any constants. And yeah, very good. Thank you. So as an easy corollary of our rainbow cycle result, we get a non-abelian version of this theorem of Sanderson-Shkredov, which has a slightly worse bound in terms of the dimension. So what we show is that, what we get as more or less an immediate corollary is that if you take an arbitrary group and you take a subset of its elements, which has a small doubling, then actually its dimension is small. And here we have this extra log-log factor, which is coming because we have this log-log factor in the rainbow cycle result as well. So let me show you quickly how this is deduced from the rainbow cycle result, just to illustrate a little bit what's going on with all of these parameters and kind of how the two are related. It's short and simple reduction that is mostly just translating the notions I just told you about into what they actually are. So here's the proof. So what we're trying to do, we are given an arbitrary subset of our group, and we are trying to show that its dimension is small. Now, its dimension is just defined as the maximum size of a dissociated subset of A. So let's take a maximum dissociated subset. Its size is the dimension of A, and our task is to show that this is not too large. Now, we are going to do this by constructing a so-called bi-Cayley graph with this S being the generator set and A being the set that we are acting on. So the vertices of this auxiliary graph are going to be auxiliary bipartite graph are going to be on the left, the elements of the set A that we are starting with, and on the right, the elements that you get as A times S, so as products of some A in A and some S in S. So the edges will just be pairs where you pick something on the left, you multiply it by something in your maximum dissociated subset, so some S, and then you take this A and A times S as an edge. So it's just the kind of bi-Cayley graph where this S is the generating set. So here the number of vertices has size A plus size of A times S, and by our assumption on doubling being small, this is essentially roughly K times A. The number of edges, on the other hand, is exactly size of A times size of S, because for any A in A and any S in S, you get one edge. So now we can define a natural proper edge coloring that comes from this being the bi-Cayley graph. So namely, just for every edge, A and A times S, we color it in the color S. So namely, we are coloring by the elements of our dissociated subset, and we are coloring an edge in the color which kind of gave rise to it from the element that actually created it. Very good. So now, what is a rainbow cycle in this proper edge coloring? Well, suppose that we have some rainbow cycle, and that if you trace it around, you are getting colors S1, S2, S3, and then up to S2L when you come back. Now, you start at some element A, you multiply it by S1, then you multiply it by S2 inverse because you're going back, then by S3, then by S4 inverse, and so on. And then you wrap around and you come back to your element A. This element A you can just cancel out from both sides. And what this is giving you is a non-trivial relation between elements of your dissociated subset. And this is a contradiction. By definition of dissociated, this type of things should not exist in us. So that means that this bi-Cayley graph has no rainbow cycles. And if it has no rainbow cycles, it cannot be dense. It has, by our result, relatively few edges. And we know what the number of edges is. It's just the size of A times the size of S. And our result is telling us that an upper bound, which is just a constant times the number of vertices, times log the number of vertices, times log the number of vertices. And as we said, the number of vertices is roughly K times the size of A. So if you plug that in, cancel out, clean up a bit, you get precisely the claimed upper bound. So this is nice, clean, simple, and gives something that I think is quite nice. And also actually in the abelian case, we can use some similar ideas to actually recover this result of Shon and Shkredov. But in the non-abelian case, we don't know. So that gives a combinatorial proof of that. But in the non-abelian case, we get this log A, and we don't know how to improve it even in the group case. So this is the result that we get. Very good. So now for the rest of the talk, I would like to tell you a little bit about the proof of the rainbow cycle result, because I think it's very interesting. It's using some nice ideas, and I'll unfortunately not be able to tell you the full proof. There are some clever things, and it's not that short. Sorry, but I do want to tell you some kind of general high-level overview and hopefully give you a picture of what is really going on in the proof. So we are actually going back to the expansion idea so that we continue this alternation between homomorphism counting and expansion. And in particular, we are using this notion of robust sublinear expansion. So I don't want to start with giving you a definition because it looks maybe a bit scary and technical, and I'd rather you look at the picture and I'll explain conceptually what's going on, and then I'll tell you the definition, which will then hopefully not look so scary. So here is a graph. I want to say that it's a robust sublinear expander if the following things happen. So I want that any subset of vertices expands in a certain way. And the way I want it to expand is that if someone comes and forbids you to use quite a bit of edges that go out of this set, I still want you to have a reasonably large, so something like sublinear, meaning 1 over polylog times size of U, many vertices that you can reach using the non-forbidden edges. So this is in some sense combining two different notions of expansion. On one hand, the edge expansion, because the number of edges that you're allowed to forbid is the amount of edge expansion that you are guaranteed, because otherwise you could just forbid all the edges and you get no expansion. And on the other hand, you're also getting some sort of vertex expansion, because I insist that you still get a pretty decent number of new vertices when you expand, regardless of, when you forbid some amount of edges. So this is the high-level picture of what's going on here. So let me now put it in kind of more precise way, just because the numbers will actually matter for us, and we are kind of working at really the bleeding edge of what you can do with this, at least as far as I'm aware. So here is the definition. So an n-vertex graph is said to be a robust sublinear expander if for any epsilon between 0 and 1, and this is just a parameter that's going to control the size of U. We're going to see that in a moment. So we have the following holds. So if you take any subset of the vertices U, so same as in this picture, and as I said, we are controlling its size by this epsilon, so the size of U should be at most n to the 1 minus epsilon. And feel free to think this as being equality and actually defining epsilon, but for certain technical reasons, it's actually easy. It makes it a bit nicer and easier to work with if I allow this to be smaller or equal. So the second thing we have is also an arbitrary set of edges whose size is bounded by the size of our U that we picked and epsilon times the average degree over 3, say. So you should think of a typical set U should have size of U times the average degree of G edges incident to it. So this is saying that we can forbid an epsilon over 3 proportion of these edges. And we should still get expansion in terms of vertices, which is of size epsilon over 3 times the size of U. So here I'm saying that the size of the neighborhood in G when F is forbidden of the set U should have size at least epsilon over 3 times U. Very good. So this epsilon, so let me just illustrate what's really going on here. So what this is saying is that if epsilon is an absolute constant, then any set of size at most n to the 1 minus epsilon should expand by a constant in term, well, we can forbid a constant proportion of edges touching the set U, namely epsilon over 3 proportion, and we still expand by some constant factor when going out. On the other hand, if you take bigger sets, so sets of size, the biggest one that really makes sense is something like n over 2. So that means that you're choosing epsilon to be 1 over log 2n. Then you can forbid 1 over log 2n proportion roughly of the edges, and you still expand by 1 over log 2n proportion of the vertices, which is why this is still called sublinear expansion. We are not always getting this constant factor expansion we do. So in some sense, small sets expand much better, but bigger sets expand by, like the linear size sets will expand by just 1 over log n factor.
Matija, in
So
particular, epsilon might depend on n, correct?
Yes. So epsilon here you can choose as you wish between 0 and 1. So 1 over log 2n makes sense. It doesn't really make sense to take it less smaller than 1 over log 2n because you're just not really getting much more information compared to the previous ones. But technically, you can get it for what we want.
But just to make sure, it's the graph will satisfy this with different epsilons, right? Not with the same one. Or you will fix epsilon before you start.
You can choose epsilon. So your first choose. So actually, so how this really works is you pick your subset U, then it has some size U, and you define epsilon so that the size is n to the 1 minus epsilon. So this is what I said here, that you should really think of this as being equality. It's just that I want to say that because we'll have upper bounds on our sets, not equalities on the sizes. So I want to say that if I have an upper bound, then anything smaller expands at least to the level that the upper bound is guaranteeing. It also allows not to worry about these things of size n over 2 and so on. So it makes it a bit nicer technically with this smaller or equal, but really you should think of it as the best you can hope for and that you should do for any set is just pick equality here and pick epsilon that way. But thanks for the questions. Good clarifications. Very good. So now these things turned out to be quite, so sublinear expansion has proved to be quite useful in the recent years, and this robust sublinear expansion is also finding quite a few different applications. So I should say that there are quite a few different equivalent definitions. So this one is somewhat new, but it's combining and actually more or less equivalent to several that have been floating around. This forbidding some amount of edges is due to Hasselgrave, Kim, and Liu, as far as I'm aware. And the way we are finding these things and this gradual expansion, like the having control on how they expand for different sizes, is something that also appeared in several papers before. So we are kind of combining these two, in particular in this one of Tomon as well. So we are combining these two things and kind of getting the, in some sense, the stronger version, which implies all the others. And you can also go either way by paying some log-logs. But really, the key property that we want from these robust sublinear expanders, and in general, that's what I like to call the path to expander lemma, which the first version of it was proved by Komlosh and Semeredy in the 1990s. So it says that in arbitrary graph G, you can find one of these robust sublinear expanders, which has, in some relative sense, roughly the same average degree. So you should think our average degree is at least some log times log if you want. So of the number of vertices, so it cancels out with this log number of vertices in the denominator. So you're getting that the average degree of this robust sublinear expander is still log times actually log of the original graph plus the big constant we had in front. We lose this factor of 3, but essentially we just pay the constant factor and we manage to pass to a robust sublinear expander and keep the average degree at a similar level as it was when we started in a relative sense. So proving this is not too hard. You just pick a correct function, density function, and then you take the subgraph of G, which maximizes it. I'll not go into it. It's a little bit technical to get it to work. And also, if you want something like this to work below log, you can choose different density functions. You will get slightly different results. And like there are also different ways of proving this by taking this, the sparsest cut and then kind of iterating on iter parts. But for us, we are just going to use, I'm just going to use this lemma. I'm not going to go into more details about it. So it just tells us that we can always find a robust sublinear expander, and we just lose some constant in the average degree in some sense. Very good. So now here is the general setup for the proof, and I'll tell you the key lemma that we need to prove. So we have an n-vertex graph G, which has average degree, something like 10 to the 7 times log n log log n. And let's also assume that it is a robust sublinear expander. So in reality, we would need to pass into a robust sublinear expander subgraph. But as we said, this really costs us just some constant in the average degree. So let me just assume that the original one was a robust sublinear expander. Very good. So now we are also given a proper edge coloring of this graph, and I'll call the set of colors C. And let me introduce the notion of rainbow neighborhoods, which are really kind of the key objects that we will be tracking. So given a vertex in our graph and a subset of colors, the rainbow neighborhood around this vertex using the set of colors C prime is just the set of vertices that you can reach by following a rainbow path, which is using only the colors in this subset C prime. So that's a fairly natural thing to think about when you're trying to find rainbow objects, and we'll see the role it plays. So I need to introduce one more thing before I tell you the key lemma, and this is the kind of subsampling notation. So we will be sampling our colors randomly, so it will be convenient to have the notion of C of P, in some sense as Gn of P just for the set C. So we are taking every color in C with probability P, and this is a random set, that's a random subset of colors that we are getting. Very good. So now here comes the key lemma that we prove, which I'll translate in words. So what it's saying is that we prove that the probability that if you look at a rainbow neighborhood around an arbitrary vertex using the set of colors which are subsampled with probability half, then this rainbow neighborhood is bigger than a bit more than a half with probability at least a half, well, more than a half. Now, why is this useful for us? Well, think about when we subsample colors with probability half, the set that we get is distributed as C1 half, but also its complement is distributed as C1 half. And since we are getting here probability bigger than a half, there is an outcome in which both the set of colors we sampled and its complement satisfy this inequality. So that means, since this is bigger than a half, that using both disjoint sets of colors, we can reach the same vertex which is not equal to V. So we can find a rainbow path from V using the subsampled set of colors that goes to U, and the rainbow path from V that goes to U using the complement set of colors. So that gives us a rainbow walk which includes this V and U, because in each part we have a rainbow and the sets of colors are disjoint. And if you have a rainbow walk, you just take the smallest subwalk that contains V, and you get, and is not trivial, and you get the rainbow cycle. So if we prove this lemma, we are done. So we really need to show that in some sense, this rainbow neighborhoods expand nicely as we subsample the colors. So now let's see how that works. So we are going to use the sprinkling method. So we are going to be revealing our random sets of colors in stages. So the probability by which we are going to reveal it is going to be 1 over log log n. So by this, I mean that every color has a chance of, if it's not in the set already, has a chance 1 over log log n times log log n to be included in the next set. And we have some 1 over p roughly. So I'm being slightly not precise with constants here, but we have roughly 1/p stages in which we are revealing this random set. So it's actually convenient to define it in reverse, but it's equivalent. You can think of it however you prefer. So the final set of colors is, so after m stages, is going to be just our C of 1/2. And then we define the previous set of colors as being just the subsample set of that we just had in the previous stage with probability 1 minus p. So that really means that for every color that was not inside of it, it has probability roughly p of getting included, and going back, every color has probability p of being excluded from the previous set. And this will be important because we are going to go both forwards and backwards in time in some sense. Very good. So let me define UI as the set that we can reach by rainbow paths from V using the colors in our set of available colors at stage I. And let me call by U the size of this set. So how many vertices we've reached so far. So in terms of a picture, we have our set UI. And because we are in a robust sublinear expander, we know that this set expands nicely or expands in a way that I just told you about. So, but unfortunately, not all edges that go out are useful for us. So there are two types of edges that go out. The first one we call free. So these are the edges whose endpoints inside of UI have a path, a rainbow path that goes to V, and which is using colors that are in the currently allowed set of colors and are not using the color of the edge. So this is really just the edge that you can append to some good rainbow path in such a way that it will witness that its other point gets added to UI plus 1. Okay, so there should be some rainbow path from this point to V that is not using the color of the edge and is using only the currently allowed set of colors. So if we subsample the color that is the color of our edge here, then its other endpoint is going to be added into UI plus 1. That's the property we want from this. Unfortunately, as I said, we cannot guarantee that all the edges will be of this form. Actually, the expansion becomes rather small because we're losing this 1/log n factor when the sets become big. So there might be just log n many edges on average going out of every vertex, and these could all be forbidden. So actually, just with this idea, you can fairly easily recover the result of Tomon with log squared times log. But let me tell you how we actually get to the log and how we go below this log squared barrier. So I'll be coloring these free edges in blue. So this is not part of our original coloring. It's just this auxiliary coloring into good edges and bad edges. So the bad edges will be colored red. So we'll call them blocked. And they're just edges which are not free. But what that means is that an edge is blocked if any rainbow path that goes from its endpoint inside of UI to V is using its color. Okay, so you cannot use it to, like if its color gets subsampled, we still cannot use it to extend because we don't have like it would break the rainbow property of the path. So this is really just the complement of what free was. So now we'll have a dichotomy, whether we have a lot of free edges or whether we have a lot of blocked edges. And actually, we will need a little bit more than just controlling the number of these things. We need a bit more information. And this is one of the key places where the expansion comes in. So what we'll need, so in the first case, is that there is epsilon du over 7 free edges, but with the property that on the right, we have max degree being equal to d, or at most d. So this, remember, we are guaranteed epsilon du over free edges going out of UI by just the definition of expansion. So this is roughly like a bit less than a half of them, but we also need this property that they're not all just coming from the fact that like you have one vertex of massive degree on the right. And you can actually get the dichotomy. The second case will be that we have that many blocked edges, but with the max degree bound actually being on the left. And you can prove that the robust expansion is guaranteeing that this is an actual dichotomy, so that we can get this control on the max degree. Again, this is a lemma that is time. It's not even technical, but it takes some time, and I'll not go into it. I hope you'll just believe me that you can split into these two cases. So now let's look at this first
The
case.
maximal degree you need because you want to count the edges and actually get a vertex neighborhood, right? Because you don't.
Yeah. So I want that when we grow, that the number of vertices grows. So if you had just very few vertices, they would be very high probability be good, but they would only be too few of them for the growth to actually work like it should. So I'll go through that now. So this is the first case. So if we have this property, so in the picture, we have epsilon du over 7 edges, and we have max degree among these blue edges being at most d. So now in this picture, we know that we need to have at least epsilon u over 7 vertices, precisely as Benny said. And let me also assume that we have precisely this many. If you have more, it's just the expectation calculation, which gives you the same outcome. But let me just, for numbers and picture maybe being clearer, assume that we don't get more than epsilon u over 7. The numbers work out exactly the same if we do get more. But what that means is that actually each of these epsilon u over 7 vertices should have roughly degree d going back to ui. Right, and d is, remember, some big constant log n over times log n, so it's like d over p, some big constant over p. So when we sample with probability 1 over log n, we are actually going to sample one of these colors, one of these d colors that go out of the vertex back into ui with constant probability. So that means that this vertex outside is getting added into our ui plus 1, each of them with constant probability. So we are getting that actually in expectation, the number of vertices in ui plus 1 is growing by a 1 plus epsilon over some constant factor, which is what we want. This is how the expansion just works without any special rainbow type things, and you get diameter being log n. Again, this is a calculation, but it can be done. There is actually a caveat here that we are only getting this in expectation, which is actually a problem because our expansion is tied to how big the sets actually are. So in order to be able to do these things and control how much we are actually expanding, we really need to have control on how big these things are. And you cannot just do concentration inequalities because you don't have enough probability to do it log n times log n many times. But what you can do is, and what we do actually do is, we are kind of careful in when we use Markov to convert this into actual probability bounds. So what we are going to do is we are going to just after every log n samples, we are going to use Markov inequality, which is going to give us some lower bound on this, or some control on the size of ui plus 1 at that time. And this control is going to be good enough for the next log n stages. And then we are going to again do it. So we need to update once in a while, because just the expectation calculation on its own is not going to work out for this, because somehow if you had the case in which you have too many vertices, in distribution, if you have cases with few and too many, then the expansion doesn't work out as you want. But this can be done. It's again part of the reason why the argument is a bit longer, because this needs to be done carefully, but it can be done. So now going back to the second case, which is in some sense more interesting here. So this is the case in which most edges are blocked. So in particular, we have epsilon du over 7 blocked edges, which this time have max degree d on the left. So here are, as I said, I'll draw them in red. So we have epsilon du over 7 of them, and we have max degree on the left being d in terms of these red edges that go out of it. So again, the dichotomy is not obvious at all. It requires proof that this actually always happens one or the other. It requires this robust expansion, but it can be done. But once you have it, we can play a similar game as we did before, at least for a second. So on the left, we need to have at least epsilon u over 7 vertices, which are incident to these red edges. And once again, we might have more of them, and that kind of helps us because we have more variables, but they will have smaller probability of actually being sampled. So in the expectation, we always get the same thing. So let me, as before, assume that we have epsilon u over 7 vertices here, so that they all have roughly degree d. And now, really the key property to observe here is that if you look at any of these vertices, they have d edges going out. So that means d different colors. And we know that any rainbow path from this vertex to our origin V needed to use all of these d colors, because otherwise these edges would not be red, they would be blue, they would be free. But that means that if when going from ui minus 1 to ui, you sampled any of these d colors going out, you actually disconnect this vertex. Right? So if we pick any color that goes out of it, and this was a new color when going from ci minus 1 to ci, then we break every rainbow path that goes from V to our vertex that we want to expand from. So what that means is that that vertex does not belong into ui minus 1. And again, since we have d things going out, probability is some like 1 over d with some constant added. That means that with constant probability, we will sample one of the, like we will have sampled one of these colors going out of the vertex here, which means it was not, with constant probability, each of these epsilon u over 7 vertices did not belong into ui minus 1. So in this case, we are not going to necessarily grow when going up. We are going to, what we get is that we are actually growing from the previous step going into the current one. And again, this is expectation calculation. Markov gives us what we want. But summarizing these two things, we are not guaranteeing that in each step you grow as we would like, but we do guarantee it in 2 steps. And this is the kind of high-level idea of the argument. So, I mean, there are quite a lot of details that I did not go into, and even some nice and clever ideas how to get around them. But on a high level, this type of either you expand in the previous step or in the current one is really the kind of the key idea behind the whole proof. So let me wrap up and mention just a few concluding remarks and some open problems which I like. So what we proved is that if you take a properly colored n vertex graph with average degree 10 to the 7 log n log log n, you can find a rainbow cycle. The most natural question here is, well, can you get rid of this log log n, since the best known lower bound is a little bit better than log 2n? And there are various constructions which are kind of making me believe that it might be possible to improve this, but so there is one coming from Hamming graphs, and that will kind of break our expansion argument and really show that you cannot do with that better than log n log log n. It doesn't work because of some silly small pictures where you'll find your rainbow cycles. And there is another example coming from group theory, which sort of doesn't work because the symmetric group is a bit bigger than it should be. And so I'll actually go and say a few words about that problem. So let me say it, and then I'll get back to why this actually gives another example, which might, well, actually it would indicate that maybe log n log log n over log 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 n might be the correct thing here, but anyway. So the open problem that I want to mention, which is actually related to this example, is the so-called, well, it's asking actually for the dimension in this additive sense that I told you about, of the set of transpositions in the symmetric group. So what that means, translated back to the words, is that we are asking for the minimum integer t such that if you take T transpositions in the symmetric group with K elements, then you can multiply them in some order to get identity. So I'm not allowing you to reuse transpositions because that would make it silly. And I'm also not, that is also preventing you from, because this is also preventing you from taking inverses, because transpositions are self-inverse, so you cannot conjugate either, which is what makes this somewhat non-trivial and slightly different than most of the things that people looked at of this flavor in group theory, at least as far as I'm aware. Now, the question here is whether this T of K is actually, well, I'm stating it here as whether it's at most constant times K log K, which is what I believe is the truth. So what we can prove is that it's at least K log K over log K, and it's at most K times log squared K. So the upper bound is an immediate corollary of the rainbow cycle result. So actually of the corollary in the group setting that we had there. The one thing to notice is that Sk has K factorial vertices. So log of that is already K log K. So this is why you're getting another log here compared to what we had previously. But it's in some sense boosting this difference of log n in the rainbow cycle result to be an actual log factor when working in this transposition world. The lower bound is coming from just taking graphs which have GERT higher than their degree. And then you stare at this for a little bit and you can see that it will actually never have one of these products. And you can do that up to this point. And in some sense, this would be perfect and prove that you need some sort of log n there divided by log if symmetric group did not have K factorial elements, which is K log K. And actually, all of the constructions we have are coming from this type of things. So the hypercube graph is just you take disjoint transpositions. And the reason why that is doing a bit better than this one is that it's only generating 2 to the K elements in the Sk. It's not generating the whole group. And similar thing happens with this slightly better construction. It's also actually just a collection of transpositions. So I think it's quite interesting in its own right. And in some sense, I feel this is a slightly silly reason that we're not getting this log K, but of course, silly reasons are sometimes not so silly. So thank you very much for your attention.
Thank you, Matija, for a nice talk. So questions?
I got one question about the reduction that you showed us in the beginning to this problem of dissociated subsets. You say that in abelian groups, you can actually get the same result of Schoen and Shkredov. But here, so what's interesting is that you get very specific relations out of this set, where you have the same number of elements with inverse and with positive powers. So I'm wondering, are you capturing other relations in this abelian case when you get the correct bound, or are you managing to capture subset sum being equal of subsets of different size?
So how that works, at least from what I remember, is that you're essentially doing, you start from a vertex and you try to you can move essentially in many different ways. So you are encoding any point that you get by the set of elements that you are using. So it's not this argument, it's not quite this argument. It also has arguably nothing to do with rainbow cycles, but like the abelian argument, but it's somewhat similar in the sense that if you had these two different subsets which evaluate to the same thing, then because of the abelian case, you can cancel things out and you will get a non-trivial relation so long as the subsets are not different. And you have only 2 to the number of generators, many different subsets that you could have taken.
Right, right. So you're managing to capture even subsets of different size, which is?
Yes. So, it's also in this definition, here we are always getting the same number of inverses and it's a special form of linear relation that we're always getting, which is actually stronger than what I said in the definition, So in the definition, I'm happy with any sort of linear relation, no matter how big the sets are. So right, so even in the kind of abelian case, it would be a linear relation if you have 2 elements summing up to 10 elements on a different side.
Oh, yeah. So I was somehow thinking that in order to get tight bounds, you need to get somehow these relations as well. But yeah, so I understand. Yeah, thank you.
I think it's good to say that, Matija, that in abelian case, there is a simple statement for which log n is known, is that if you want to get a cycle with a unique color, then the answer is indeed log n. It's not difficult to prove. And I think that's enough for abelian case.
Yeah, you can do that. You can do that here, and that's a result of Benny and Oliver. They have a nice result, which because
it's a result in the original paper.
But actually, sorry, say.
I am saying if you have graph with n log n edges and it's properly colored, there would be a cycle in which some color would be unique. And I think that's enough to prove the abelian case.
True. So it's, yeah, so it needs to be a slightly different definition of, because you might get 3 times something technically.
Yeah, odd. Okay, yeah.
But that is actually called Freiman dimension as well. So that also exists. So it's, yeah, I mean, but you are correct. It's like it's morally doing the same. But yeah. I mean, yeah, but you can get it here by just like slightly different argument that is just encoding your paths wherever you go, and you need to end up in different vertices for all different encodings. And so it's a slightly different argument, but yeah, it will also give it to you here. But yeah, thanks.
More questions? If not, let's thank Matija again for a beautiful talk. Right, and hope to see you all next week. And next week it would be Raiko Nenadov. If I'm not mistaken, I will send the announcement later today. We can stop the recording.